Okay, so today we're going to be talking about the total internal reflection of light, which is actually subtopic 6.2, or not really subtopic 5.3. This is old syllabus lah. Okay, this is subtopic 6.2. Okay, we say hello and welcome again to my horrendous handwriting. But these slides follow very closely to your handout. So if you have your handouts with you, it's a good idea to take them out now lah. One of the major applications of total internal reflection is the sparkle of the diamond. Okay, so of course the question is, how do you know that if you, like girls, one day when you get engaged or get married, right, and if your future husband or your, or whatever, gets you a diamond ring, you want to know, like, oh, is the diamond ring real or is the diamond ring fake? Okay, so one of the ways that we do this as physicists, is to look at the total internal reflection lah. Okay, one of the main applications of total internal reflection actually is the sparkle of the diamond. Okay, and it's very obvious. Okay, both diamonds and glass actually sparkle, but the sparkle of the diamond is actually a lot more, more shiny lah compared to glass. Okay, but before we begin, I just want to slowly recap the three ways. Okay, the other day in the previous video, we looked at three ways to count refractive index. Okay, one is sine I over sine R. Okay, which is the incident angle and the refractive angle. Second one is the real depth over the apparent depth. Okay, so this is big H over small h. And the third one, I'm not sure whether I mentioned this in the previous video, is the speed of light in the air. Okay, over the speed of light, okay, in the medium. Okay, now no matter what happens, whenever you calculate refractive index, always remember that the bigger value always goes on top. Okay, regardless of what situation you're in, and this is going to come even more apparent today lah. Okay, the bigger angle we always put on top. Why? Because the refractive index must always be bigger or equal to 1. There is no refractive index that is smaller than 1, because refractive index 1 refers to the air around us. Okay, so if you calculate, then you get the refractive index as 0 point something, then something is wrong. Okay, you've terbalik the value. So always remember this, the refractive index must always be bigger than 1, and because of that, the bigger value must always be on top. Okay, it can be 2 point something, it can be 3 point something, as long as it is not 0 point something. The moment you get 0 point something, it's a red flag. Okay, so let's talk about total internal reflection of light. Okay, previously we also know that the movement of light, okay, the movement of light in certain mediums, okay, will cause it to refract lah. Okay, and generally, if you're going from a less optically dense to a more optically dense, okay, material, say for example, if you're going from air into glass, okay, so the refraction, okay, will be nearer to the normal. And likewise, the other way, okay, if you're going from more dense to less dense, sorry, I'm using a different pen, which makes my handwriting 10,000 times uglier. Okay, for example, if you're going from glass to air, okay, air is less optically dense, glass is more optically dense. So the refraction, hold on. The refraction, okay, will be away from normal. Okay, all this we covered in the previous subtopic. I hope that all of you here, okay, have already watched this in the previous video lah. But there are two directions in which the light will move after refraction, either nearer to the normal line or away from the normal line. So in this case, we have a light ray that is inside the glass and is going to go out into the air. So as you can see here, the angle is smaller, and here the bigger is angle. So we say this is moving away from the normal line. Okay, so what happens to the light when it enters from a denser medium to a less dense medium, more to less will be away from the normal line. So the intensity of the refracted ray, this one, refracted ray, and the reflected ray, if you look at it, this is a strong refracted ray and this is a weak refracted ray. So the refracted ray is brighter, or the intensity of the refracted ray is bigger than the reflected ray. Okay, so there is actually a little bit of reflection, but most of it is refracted. Okay, and we find that the refracted ray is stronger than the reflected ray. Now relate the incident angle to the refracted angle. This is from the previous subtopic. Okay, the bigger the incident angle, the bigger the refracted angle. This is standard. Okay, it's directly proportional. Okay, so this is I don't think this is in your notes, but just take a look. Okay, the greater the incident angle, the greater the refracted angle. This is something we established in the previous lesson. Okay, for example, this green one has a very small incident angle, and then the refracted angle is like this. But when we make our incident angle bigger, so the red one is this. Oh, sorry. Astaga, kejap, kejap, kejap. So the red incident angle is this. Okay, and we find that the red refracted angle gets even bigger. So the further and further you go away from this normal line, okay, this is the normal line. Okay, the further and further you go away from the normal line, the further and further it becomes. Okay, until a certain angle, okay, the further and further you go away, the bigger and bigger the refracted angle becomes. Until a certain angle where it will finally reach 90 degrees. It will be such a refraction that is like totally 90 degrees to the normal. Okay, the angle of refraction approaches 90. So this is what we want to talk about today. Okay, number two, the diagram 2 shows as the angle of incidence increases, the angle of refraction also increases. So what happens to the light ray when the angle of refraction reaches 90 degrees, like this? Okay, so we say that it refracts on the glass air boundary. Okay, dia punya sempadan itu, it refracts there. Okay, and it is a 90-degree refraction. Previously, all the refraction is in the air. Okay, tetapi when you hit the 90 degrees, then we say that the refraction is ngam-ngam on the boundary of the glass and the air. Okay, and so this is the limit of the light ray that can be refracted in the air. Okay, the angle of incidence in the denser medium, okay, in the glass, at this limit is called the critical angle. Okay, and in your ruangan over there, the definition of critical angle is the incident angle. The critical angle is the incident angle over here that gives you a refracted angle of R equals to 90 degrees. I feel like I'm writing in my right hand. So horrible my writing. Okay, this is the definition of the critical angle. Okay, the critical angle is the incident angle which will give you a refracted angle of 90 degrees. This is a new concept, critical angle. Okay, and why is it critical? Because it's on the boundary. Less than the critical angle, in this case, less than the critical angle, you will get refraction. At the critical angle, you will get 90-degree refraction. So the question is, then again, what if you increase the this one? Okay, that's what we talk about in a while. So the critical angle, as I said just now, is the incident angle that gives you a 90-degree refracted angle. Okay, and the refraction is on the boundary. Okay, anything beyond the boundary is a different case altogether. Okay, so if we follow this diagram, notice we get bigger and bigger angle, kan? The refraction angle gets bigger and bigger. And then of course, when you hit the black color one, the refraction becomes 90. So the question is, what if I have an even bigger incident angle beyond the black color line? What happens to this one? Will it go this way or will it come back and be refracted? Okay, and that is why we call this the total internal reflection. Okay, in this case, where the incident angle is bigger than the critical angle, okay, the light will be reflected back into the glass. And it's very logical. Okay, the light is reflected back in the glass because The pattern follows green go to green, red go to red go to red, brown go to brown, black go to black. And so this small line over here must continue the pattern of going upwards, okay, which will be like that. Okay, and so we find that this is a kind of reflection, okay, which we call total internal reflection. Okay, so when the light gets reflected in the glass, we call this situation total internal reflection. And there are two conditions where this phenomena can occur. Number one, the light must travel from a denser medium to a less dense medium. For example, an example of a denser medium will be glass. Okay, and a less dense medium will be air. So light travels from glass to air, then can. Okay, so if you look at this diagram, here is air, here is glass, and here is air. Okay, the light wants to travel from the glass, mau keluar pergi air, tapi tidak jadi. Okay, dia jadi total internal reflection. Okay, that's the first condition. Second condition, the angle of incidence must be bigger than the critical angle. Because as we said just now, at the critical angle, if the angle of incidence is ngam the same as the critical angle, the refraction is 90 degrees. If the angle of incidence is less than the critical angle, then refraction happens. But if the angle of incidence is bigger than the critical angle, then total internal reflection happens. Why is it called total internal? Because there is no longer any refraction. Okay, and again, I hope to show you this when you come for the face-to-face. I was saying just now that when refraction happens, there's a little bit of reflection. Okay, a little bit of reflection will happen. Okay, and as the angle gets bigger and bigger, the refraction also gets bigger and bigger, and the reflection also will happen lah. But when total internal reflection happens, okay, there's totally no refraction. That's why it's called total internal reflection. Okay, all the light is totally reflected, and that brings us a lot of applications which we'll talk about in a little while lah. Okay, but the main idea behind total internal reflection, and if you understand this, then you kind of understand the whole subtopic already, is that there are two conditions in which this must be fulfilled in order for this to happen. Number one, the light must be traveling from more dense to less dense, glass to air, okay, or glass to oil, contohnya. Okay, more dense to less dense. The second condition is the angle of incidence must be bigger than the critical angle. Less than the critical angle, refraction. At the critical angle, 90 degree, boundary refraction. Okay, more than the critical angle, then reflection. That's why the word critical angle is important. It's so critical, because less than that, something happens. More than that, something happens. Ngam critical angle, another thing happens. Okay, so it's like the angle that changes everything about light. Okay, critical angle. Okay, so when we come back to school, well, which I hope you all come back, okay? I hope to be able to do this with you all. Instead of using a ray box, we will probably use a laser pen, okay? Because I think it's easier to see with a laser pen, okay? And we'll experiment with this, okay? Just short, simple experiment. You can keep this section in your notes first. Maybe bring back the notes for our class so that we can answer this together, For example, okay, if the I is incident angle. If the incident angle is less than C, critical angle. For example, if the critical angle is 42. So let's say this angle over here is, let's say 35. 35 is less than 42 lah. So then refraction happens. If this incident angle is ngam 42, and you already know that the critical angle is 42, so then we say boundary refraction happens. Okay, the refraction happens at the boundary. If this angle is more than 42, say for example 50 lah, okay, 夸张一点 lah, okay, make it 50. If 50 is more than 42, so total internal reflection happens. Okay, this is really the summary of this entire subtopic. As I was saying at the very beginning, which I rubbed off already, how the three ways to calculate refractive index: sine I over sine R, real depth over apparent depth, speed of light in the air over speed of light in the medium. Okay, no. Speed of light in the air, speed of light medium. Okay, so we also need to know how to calculate refractive index, okay, by using the critical angle. Okay, so in this case, light travels from dense to less dense medium. Okay, so referring to this figure, since the refracted angle is R, okay, this is the refractive angle and this is the incident angle, okay, which is now C lah. Okay, and again, I know this looks very funny. Apa ni? Kenapa bukan I di atas? Kenapa R di atas? Because, as I said just now, when you calculate refractive index, the bigger angle must be on top. Okay, and obviously 90 degrees is bigger than C. So we put the 90 degrees on top. Okay, and we call the incident angle as C, the critical angle. So when you calculate sine 90, if you press your calculator, sine 90 will give you a value of 1. And this is the fourth and the final way, okay, that we calculate refractive index. The relationship between the critical angle and the refractive index. The bigger the critical angle, the smaller the refractive index. Okay, so if you want a big refractive index, your critical angle has to be very small. If you have a big refractive index, okay, a big N, okay, means you have a small C. Okay, if you have a small critical angle, the implication of this is that total internal reflection easily occurs. Okay, if your critical angle is small, then total internal reflection are very easy to occur because you don't need such a big angle for the reflection to occur. And that is helpful, especially if you want things to, if you want to use total internal reflection for the applications, which I will talk about in a little while. Okay, but this understanding is very important. A small critical angle means total internal reflection easily occurs. And at least in our syllabus, we want total internal reflection to easily occur. Okay, so that our lives are 10,000 times easier. Okay, we will talk about this in a little while. The reason, actually, I should say, the reason why I can do online class with you is because of total internal reflection, honestly. Okay, if there's no total internal reflection, then we cannot do online class. So I guess if you want to blame anything for why you have to come for online class, you should blame total internal reflection. Okay, blame all the physicists that came up with all this. Why do they have to make our life so difficult? Okay, let's do a couple of exercise questions so that we get to know this. The refractive index of water is 1.33. So 1.33 refers to N. Okay, so what is the critical angle of water? Kita mau cari C lah. So the formula we have is N equals to sine 1 over sine C. Okay, you know what? Give it a shot. Substitute N in substitute 1.33 over here. Can you calculate sine C? You need to shift sign. Okay, so if you did this, if you substitute correctly, okay, bring the 1.33 ke bawah, 1 over 1.33, this will give you how much? Sine C equals to 1 over 1.33, 0.752. Okay, lebih kurang lah. Then you shift sign, okay, shift sign 0.752, you should get around this figure lah, 48.75. Okay, quite an easy formula to use, okay, don't worry about this, quite easy formula. Okay, let's go with the second question. Figure 2 shows 3 light rays, X, Y, Z. Okay, incident angle at incident at the midpoint of AB over here, O. Okay, the critical angle is 42. Okay, then they cakap NOZ is 30. Okay, so this now tests our understanding. Okay, this is 30. Okay, NOY, this is 42. Okay, and then the third one is the whole thing over here. This is 60. Okay, so draw the direction of rays X, Y, and Z from O and label them as X prime, Y prime, Z prime. Okay, don't worry. So let's talk about Z first. The angle is 30. So the question you should be asking is it more or less than the critical angle? Obviously, it's less lah. 30 is less than 42. So if it is less than the critical angle, what's going to happen? Refraction or reflection? It's going to be refraction. Okay, so it's going to be refracted lah. It's going to be refracted lah. Okay, so doesn't have to be exact science, just, can simply draw, don't worry, as long as you show the refraction. The second line, NOY, is 42, which is ngam the same as the critical angle. So what happens if the critical angle and the incident angle is the same? We call this boundary refraction. Okay, so this is what's going to happen. It's going to refract at the boundary. Okay, and of course, the third one is 60. 60 is bigger than 42, bigger than the critical angle. So bila the angle of incidence is bigger than the critical angle, what's going to happen? It's going to totally internally reflect. Okay, that's it. I mean, well, that's it for the basics lah. Okay, the basics of this subtopic. Okay, once you understand this, everything else should be quite okay. All right, let's give number 3 a go. Okay, predict what will happen. Angle here is 55. The refractive index is 1.3. Okay, so if you are given the refractive index and then you want to know, okay, is this going to go, there are only 3 places it can go. Either it refracts, or boundary refraction, or critical angle. Tapi mana satu? And in order to know this, you have to know the critical angle. So this is a combination of the first and the second question. Okay, so find the critical angle first. How much is the critical angle? Use n equals to 1 over sine c. Okay, give it a go. So if you do the calculation, you will get, okay, you will get the angle about 50 lah. Okay, Jen over here says that it's 50.28, which is fine. Okay, but basically the critical angle is smaller than the incident angle. Sorry, the incident angle is bigger than the critical angle. So bigger than the critical angle means what? It's going to reflect. Okay, that's all you need to know. I guess the word critical angle is important now because it's so critical. No? It tells us a lot of things. So how to calculate the critical angle is a very important skill in this subtopic. Okay, next question. Okay, same thing. Refractive index of glass is 1.51. Determine the critical angle of the glass. Okay, let me give you the formula again. N equals to 1 over sine C. Okay, and then tell me, what happens to the ray of light after this? Okay, go ahead. 20 seconds. Calculate the critical angle first. This is the working, of course. Then you get C is about 41 point something or 42 lah. Okay, generally. I don't know why this particular slide, makes everything smaller. Okay, so let's consider what happens to the ray of light. Of course, since the ray of light is now perpendicular to the boundary, okay, so it's just going to go straight through first lah. Okay, but once it goes straight through, it hits the boundary, which is a little bit sengit. There's an angle over here. So what you need to do is you need to draw a normal line first. Okay, draw a normal line, and again, all normal lines are 90 degrees lah. Okay, coordinate geometry teaches us that. Okay, normal lines are 90 degrees. So then the question here becomes, what is the incident angle over here? Okay, what is the incident angle? Okay, if you follow this, this is a triangle, this is 45, so this must be 90 degrees lah, because it's a straight line, right? So if this is 45, therefore this is also 45. And if this is 45, this is also 45, because 90 degrees over here. Okay, so our incident angle is 45, but our critical angle is 42. So where is the light going to go? Is it going to be refracted, boundary refraction, or reflect? Okay, of course, the answer will be reflection. Okay, reflection. It will totally internally reflect. Okay, and this, okay, fun fact which you're going to learn in a while, okay, and this is a very important application, okay, of the periscope. Okay, periscope is the one yang kita pakai di submarine kan, yang mau tengok kalau if you're in underwater, then you want to see what's happening, right? So we use periscope. Another one is binoculars. Okay, binoculars also use this concept, total internal reflection. Another one, slightly closer to home lah. I don't know how many of you have binoculars. DSLR. Okay, the DSLR camera is a very, very important, the total internal reflection is a very, very integral part of the DSLR. Okay, so we'll come to this in a little while. All right, let's look at this. The diagram of light shows a light ray traveling from the air into a glass prism. Okay, what is the critical angle of the glass? So let's consider this first. Da, da, da. Okay, what is happening over here? The light goes from here, then goes here. We call this boundary refraction. Boundary refraction means this incident angle is actually the critical angle. Okay, because boundary refraction is happening. So then the question of course is, macam mana kita mau kira ini? Okay, so after very, very complicated calculation, actually it's just 50 degrees lah. Okay, take some time to figure it out now. Okay, just extend this line all the way to the bottom over here. Astaga, what the horrendous is that? Okay, you can figure this out, quite easily done. Okay, don't worry about this. I mean, not say don't worry lah, but you know, you can figure it out. This is 50 degrees. Okay, so the angle is 50 degrees. Okay, take some time to figure it out now. So let's take a short break from all the writing, not a break from the class, sorry. Take a short break from the writing. And let's take a look at this video if I can find this one. Oh, okay. So as you can see, actually there's somebody shining the light lah. Okay, there's somebody shining the light from the back of the bottle. Okay, and technically, if you shine the light is supposed to go through, right? Okay, because light travels in a straight line. But we find that the light doesn't penetrate through the water. Instead, the light follows the direction of the water. Actually, this is clearer. Okay, you find that the entire water is lit up by the light. Okay, padahal if you shine a torchlight in a straight line, kan, the light should actually come out over here. Kan, tiang like this. Astaga, sorry. The light should actually travel in a straight line out through the whole macam tu. But we find that no, the whole thing got light over here. All this got light. Okay, and so the question is, why is it that the light, although it is traveling in the water, why doesn't it come out of the water? Light naturally should go in a straight line. Okay, so we call this situation an example of total internal reflection. The light is being reflected inside the water. Okay, and that's why you can do this. Okay, I think if you come back next week, we can try to do this. It's very easily done. We have a lot of laser pens. Okay, we just get a lot of beakers filled with water, and then you fill this, and then you can shine the torchlight and see lah. Okay, see for yourself the total internal reflection. Okay, remind me if we don't do this, let's try to do this lah. Okay, so this is don't worry about this. This is just extra notes. Okay, as the angle of incidence becomes bigger, these are three important things that happens lah. Okay, the refracted ray becomes dimmer, the reflected ray becomes brighter, there is more reflection. Okay, and the angle approaches 90 degrees until finally a refracted ray can no longer be seen. Okay, just extra notes. So this is a very prime example of total internal reflection. Okay, look at this. The light is shining from here and it is being totally internally reflected. Okay, and there's some refraction over here also lah. Okay, but quite a majority of it is already totally internally reflected. Another example is how you can see the refraction of the tortoise under the water when you're in the water, of course. Okay, so this is also an example of total internal reflection. Okay, and so we're coming now to the part of the application now, and this is the part where there's going to be a lot of writing. Okay, so the first part is understanding what is total internal reflection. The second part is the calculation, and now we come to the application. Number one application, okay, is this thing called mirage. Okay, mirage dalam bahasa Melayu is logamaya. Okay, so on a hot day, if you are, let's say for example, if you're standing in front of All Saints when there's no car, okay, if you're standing in front of All Saints when there's no car and it's a very hot day, if you look very, very far ahead, actually you can see kind of like a pool of water. Okay, this is actually even more clearer in the desert lah. But well, I guess in front of All Saints also, you can also say it's kind of a desert lah. So, but the problem is you can see the pool of water there, but when you go nearer to the water, the pool of water like disappear. The question is, how does this phenomena occur? Okay, let's take it step by step. There are four, 8 points, I think. Okay, on a hot day, compare the temperature of the air at the higher level and near the road surface. Okay, obviously the air at the higher level is cooler. Okay, because I know it's nearer to the sun, but there's also hot air. Sorry, the land. Okay, you remember that specific heat capacity of land is lower. Okay, so hot air is easily generated in the this one lah. Okay, at land. Wow, there's still people coming in now. It's okay, good. Okay, so the air at the higher level is cooler. Okay, second point, compare the density of hot air and cool air. Of course, cool air is denser lah. Okay, we learned this in the previous, I don't know how many topics ago lah. Okay, hot air is less dense than cold air. So, what happens to the light ray from the sky, which travels from dense to less dense? Remember, more dense to less dense, it travels away. It refracts away from the normal line. Okay, again, taking from subtopic 6.1, which was 6.1 very important. Okay, because we bank on 6.1 to understand 6.2. Okay, next, incident angle will increase. So compare the incident angle with the critical angle. We will find that as the light rays come nearer and nearer to the hot air, the incident angle is going to be bigger than the critical angle. Okay, so, and when the incident angle is bigger than the critical angle, we learned this just now, total internal reflection will occur. So if the observer's eye is in the correct position, at the right position, he will see a pool of water appearing on the road surface. Okay, so this is the actual explanation lah. I think the black book also gives us this. Okay, 1, 2, 3, 4. Incident angle bigger than the critical angle, total internal reflection occurs. Point number 2, the light is reflected towards the eye of the observer. Point number 3, the eyes interpret the light coming from the road and not from the sky. Tapi sebenarnya the light comes from the sky. Or in the sense, the cloud of water is from the sky. And so finally, the observer will see the image of the sky as a pool of water. The image of the sky is seen as a pool of water appearing on the road surface. So this is an example of what I was talking about lah. Okay, the mirage. Okay, from very far away, it looks like there's a lot of water over there. Then when you go nearer to the camel or you go nearer to the car, suddenly the pool of water disappear. Okay, so what we're actually seeing is the reflection of the cloud in the sky. Okay, and of course, this is the explanation lah. Okay, but of all the points, this is the this is the main and important point. Okay, and for exam purposes, these two always comes together. Okay, incident angle bigger than the critical angle, total internal reflection occurs. When it reflects to the eye. Okay, yalah, habis kamu yang observe kan, so of course it will reflect to the eye lah. Okay, so the example of mirage. Okay, second application is the application of rainbow. Actually, rainbow is an application of 3 phenomena. Okay, but the main one is total internal reflection, which is why we never discussed rainbow until now. Okay, a rainbow is a colorful natural phenomenon. When sunlight shines on millions of water droplets, we see a multicolored rainbow. Okay, so name the phenomenon. Okay, which is the separation of light into colors. Okay, so this is different. The separation of light into colors is called color dispersion. Okay, this is just an extra fact. This dispersion of color lah. Okay, and it's something that is very unique to rainbows. Okay, because it's very rare that we actually see color dispersion. Rainbows is one of the ways we see it. Okay, the 3 light phenomena which produces rainbow is dispersion, refraction, and total internal reflection. The combination of those 3 gives us the thing that we call the rainbow, which we know it as rainbow lah today. Okay, so then the question is, what happens when the white light enters the raindrops? Okay, so how do we connect this dispersion, refraction, and total internal reflection together? So when light enters the raindrops, it will be refracted and dispersed into 7 colors. Dia akan terbias dan lepas tu tersebar okay, to 7 different colors that are inside the raindrops. Okay, as you can see over here lah. It's a little bit smaller. Let me show it to you. Okay, as you can see over here, when the white light enters the raindrop, it will disperse and refract into 7 different colors. But because this is more dense and outside is less dense, and the critical angle of water droplet is actually very small, so it will totally internally reflect. And then when it hits over here, it will refract, and that's how you get the 7 colors of the rainbow. Okay, so the next part now, what happens when a dispersed light hits the bed of the raindrop? It will total internally reflect. And after it totally internally reflects, it will be refracted again as it leaves the raindrop. And this is what we see. Okay, the refraction of the 7 lights is actually what makes the rainbow. Okay, so in order to explain the rainbow, you need to think about 3 phenomena. Okay, when it enters the raindrop, it disperses and refracts. And then it will totally internally reflect the first time, and then the second time it will refract. Okay, so the colors of the rainbow run from violet along the lower part of the spectrum to red along the upper part lah. And usually rainbow, red is the one that we see the most lah. Okay, and I hope you remember from the previous topic, the reason why we see red the most is because red has the biggest wavelength. Okay, so all these are somehow connected lah. Okay, so the first application is mirage. The second application is rainbow. So these are what we call natural phenomena. Okay, no need machine or anything. It occurs in front of us. Okay, it's natural phenomena, and always a reason to be thankful for lah. Okay, let's talk about machines or man-made products that use total internal reflection. The first one is the prism periscope. Okay, so the prism periscope, I think I have one or two. I have one mirror and one prism. Okay, which I can show to you. Last year, our students, this year Form 5 lah, they made the periscope. One of the groups lah. Okay, made the periscope. So I guess I can show it to you when you come back next week lah. Okay, the most important thing is that in the periscope, okay, so this is the submarine lah, and then orang tengok di sini kan, then dia pegang tu dua benda, then dia pusing-pusing untuk tengok lah. So name the component that is important to build a periscope. You need 2 45-degree glass prisms. Okay, it has to be a 45 degree, not the 30-60. The 30-60 tidak boleh. 45 degree is the best. Okay, 2 45-degree glass prisms. So what is the incident angle? The incident angle is 45. And generally, the critical angle of glass is 42 degrees. Okay, so when you compare the incident angle and the critical angle, sorry, this should be C, not R. Okay, compare the incident angle and the critical angle. 45 is bigger than 42. So the incident angle is bigger than the critical angle. And again, our understanding of this, if the incident angle is bigger than the critical angle, what happens? It will be total internal reflection. Okay, notice that I will be saying this again and again and again. There are only 3 things only: refraction, boundary, or total internal reflection. Okay, incident angle bigger than the critical, total internal reflection will happen. Okay, the next part is a drawing. So take out your ruler and your pencil. Okay, and let's draw this together. Okay, I'm going to start with K. Okay, I'm going to start with line K. So when K hits the prism over here, we saw from the drawing just now, if you remember from, what was the question just now? Let me see. If you remember this question just now, okay, when it hits, it will fall back. I mean, it will reflect lah. Okay, so likewise for K, this is what's going to happen to this one. Okay, K is blue color. Then when it hits here, it hits more than the critical angle again. So it's going to go this way. Okay, so that's what happens to light ray K. Totally internally reflect 1 time, totally internally reflect 2 times. Okay, and likewise with the light ray L, when it hits here, it's going to reflect 1 time. And then when it hits here, because it's saying it, and the angle is bigger than 42, it's going to reflect again. Okay, so this is a periscope drawing. Okay, so the characteristic of the image form will be virtual, upright, and same size. I will talk about the characteristic of the image in the next subtopic. Okay, this will become more important now. For now, just remember it as virtual, upright, same size. Okay, this is a very important point. Okay, I want to highlight this. Two advantages of using prism periscope instead of mirror. Why is it that here we use a prism instead of mirror? Because mirror also reflect, ma. Kan? Why do we use prism? Why is it better to use prism? Why are prism periscopes actually more expensive than mirror periscope? Okay, so number one, the image is brighter because all the light energy is reflected. And the reason for this is because total internal reflection happens. All the light is totally reflected. There's no light missing at all. Like it doesn't disappear into this one. And the second reason, two advantages, sorry. The second advantage is the image is clearer because all the light is reflected, ma. So the image becomes clearer and you don't get like, double or triple images, lah. Okay. In the mirror periscope, because it's so unpredictable, because of the kind of material it is, so you get more than one image. Okay. And it's very confusing, lah. Like, if, for example, you want to see whether if you're spying on an island, you want to see how many people there are on the island. You want to know exactly how many people there are. Like if there are 10 people, there are 10 people. You want to see, how come, like got 10, like got 20, susah. Okay, so we say that two advantages is the image is brighter and the image is clearer. Okay, but of course, prism periscopes are more expensive. Like prisms are generally expensive because of the glass that you use. Okay, so that's the first one. The second one is binocular. Okay, binocular is everybody's favorite thing when you want to spy on people. So the use of the binocular is not to spy on people, it's to see distant objects. What happens as the light ray enters the binocular? Look, the light ray enters, ping pong, ping pong, ping pong, all the reflection happens lah. So there is total internal reflection. Multiple total internal reflections. Okay? And you get the same characteristics. Virtual, upright, same size. Sorry. Now let's go to the drawing. Now, compared to the periscope drawing, which I feel is more important, binocular, well, I think if you can kind of guess what's happening here, you know that binocular is a real total internal reflection party lah. Okay, so this is what happens to light ray number one. Ping, pang, pong, pang. Okay, that's what you get. And then the second light ray, the red color one, okay, it'll be ping, pang, pong, pang. Okay, so that's how you get this. Okay, the arrangement of the binoculars is also pretty interesting. And this is only in one eye. Okay, so imagine binocular is two sides, right? Two sides. So there are actually four prisms in the normal binoculars. Okay, that are arranged in such a way where all the reflection happens internally and you get a very nice yeah, you're right. Actually, it may be magnified, it may be bigger, lah. Okay, but generally what we want to know is that it's same size. Usually if the object becomes bigger, it's probably because there's another lens over here lah. Okay, there's another lens over here that magnifies the image. Okay, but right now we're not interested in that lah. Okay, right now we're just interested in the total internal. The last one is the fiber optics. Okay, by far the most important application of total internal reflection is fiber optics. And I'm leaving this to the last because the applications of fiber optics is very wide. Okay, the two main uses of fiber optics is in communication and medicine. Okay, if you remember earlier in the class, I said the reason why we can have online class is because of fiber optics. Okay, nowadays the internet is fiber internet lah. Okay, and it comes from this usage of fiber optics. Okay, communication and medicine, two most important ones. Now the material for fiber optics, very interestingly, is actually glass. Okay, I know when we think of glass, kind of it's like, oh, glass is breakable, blah blah blah. But actually, interestingly, fiber optics is made of glass, and there are actually two layers into it. Let me see if I can show you. Okay, so this is an example lah. Okay, of fiber optics. Okay, and if you see, yang this bulu-bulu, sorry, I don't know how to say that. Okay, this bulu-bulu thing, right? Okay, actually it's made of two layers. There's a layer of plastic or sometimes it's rubber outside that covers the glass layer on the inside. So there are two layers. The inner layer, which is glass, and the outer layer, which is like the protective cover lah. And the most important thing is that the inner layer has a very small critical angle. Okay, if you remember, I said just now, small critical angle means very easy for total internal reflection to occur. Okay, and that's why you see the light traveling from here. In a sense, what we were seeing here just now, okay, what we were seeing here just now is an extension of the fiber optics. Okay, the light travels internally in the water. In the same way with the fiber optics, the light travels internally in the fiber optics. That's why you see all this lah. Okay, this is the fiber optic cable. This is the, what is this? The perhiasan thing lah. The decorative thing that, yeah, anyway. Okay, so compare the density of the inner core Q and the outer cladding P. Okay, of course, the density of the outer cladding is smaller than the inner core. Glass has a very big optical density. Okay, compare the refractive index. The refractive index of Q is bigger than P. Huh? Okay, page 132 and 54. The idea is there lah. Okay, page 54 or page 132. All the explanations that you need about fiber optics is there. There's nothing to copy here because everything is in a black book. But the idea is this: the inside density and the inside refractive index is bigger than the outside. Secondly, because the inside refractive index is bigger, so the critical angle is smaller. Critical angle smaller means total internal reflection can happen. So what will happen is when the light tries to go out, tak boleh because the refractive index is so big. Critical angle so small, so it will reflect. Cuba mau keluar again, tidak boleh. Reflect, 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 reflect. Okay, all the way until the end of the cable lah. So explain why the light ray experiences total internal reflection, the two main factors. Okay, the incident angle is bigger than the critical angle. That's why total internal reflection happens. So the advantages of fiber optics, okay, number one is thinner and lighter. Number two, you can send more signals at one time. And number three, very little loss of energy because everything is totally internally reflected. All this is in the black book in the 2 pages that I mentioned just now. Okay, so this is one example of use in communication. Okay, I'm talking about this, sorry. This one is communication, like your fiber optic cables, inside there is all this lah. Okay, seberkas lah semuanya. It's not just one single wire. It's many wires and then they wrap it in another, outer layer. Another one is this, okay, for use of medicine. Okay, so what we call this endoscopy lah. Okay, so if you notice over here, the guy put the optical fiber in the nose. How fun. Okay, put in the nose and then, go and check whatever it is that you want to check lah. Okay. Another one is nowadays, when people get appendicitis, appendicitis kan, dia punya appendix rosak kan or gets inflamed. So last time, it used to be they will cut open the stomach lah and then, this big operation lah. Now you can just use fiber optics and do it, by using the endoscope. You just remove the appendix with very minimal invasion lah. And of course, the most famous one is colonoscopy lah. Okay, no prizes for guessing where this goes in. It's true. Okay, kalau bronchoscopy, bahkan mau tengok the sistem pernafasan going through the nose, the leg going through the leg. The colonoscopy, well, I will leave it to your imagination lah. Okay, where do you think this fiber optic goes in from lah? Which hole in your body does it go in from? Okay, anyway, medicine is fun. Okay, the last and the very last thing, because I started with this question, what makes a diamond sparkle? Okay, so I want to end with this question and to end our class today with this answer lah. So the reason why diamonds sparkle is because the refractive index of diamonds is very high. Okay, refractive index of diamonds very high means the critical angle very low. This is also in your black book, don't worry about this, okay? Critical angle very low means total internal reflection easily occurs. And that's how you know, ladies, okay, a real diamond from a glass diamond. Sorry, a diamond ring, a real diamond ring from a glass ring. Okay, because diamond, the critical angle is 24. It's a very small angle. Glass is 42. Okay, high critical angle of glass, very, very hard to reflect. Small critical angle, very easy to reflect. Okay, so which is why diamonds are expensive, because it's very hard to find materials with very small critical angles. Okay, so if you have a diamond ring, and now I realize I'm actually talking to 17-year-olds. If you have diamond rings, what are you doing in school? But you know, if you have a diamond ring, cherish the diamond ring. Okay, and remember that diamond rings have very, very small critical angles. Okay, one last word I want to say about diamonds, and it's pretty interesting lah. Okay, that this is the main feature of the diamond. When you look at the surfaces of the diamonds and the glass, microscopically, like if you put the glass and the diamond under the microscope, actually we find that glass is a lot smoother. It's not entirely smooth, but it's a lot smoother than diamonds. Diamonds, although they shine, but they're actually very rough. Okay, but interestingly, it is the rough surfaces that brings out the most shine. Okay, so all this to say, okay, that I guess the brightest things in life come from the roughest surfaces. Okay, so if you're going through a challenge right now, like for example, surviving this extra class, stop clapping. Okay, just remember that this is just one of the rough surfaces that you have to go through, so that one day you will shine bright like a diamond and get your A plus for the physics SPM. What I would like you to do, okay, if you have done through this class, don't forget the progress report later. But our next class will be on Wednesday. Okay, will be on Wednesday. I'll let you know the time later. But what I want you to do is go through the tutorial 6.2. Sorry, the tutorial 6.2 questions in your workbook. Okay, and then send the picture to me as proof lah that you have finished it. Okay, so this is an ongoing thing lah. So if you come for online class, the good news is you don't have to watch the video anymore unless you're missing any notes. Go ahead and answer this, and then I will see you all on Wednesday.